Hello. Today we're going to take a look at certain types of integrals that we previously wouldn't have been able to compute. And these things are called improper integrals. There are two particular types of improper integrals. We'll define them in general today and start looking at how to evaluate the first type, excuse me, and then next class we'll look at how to deal with the other type. And as we go through the video, please pause whenever you need more time with stuff since you're not in front of me. I'm not sure how long certain things will take you to do, so please pause as we go through this. If we want to compute the integral from a to b of f of x dx, and we saw a whole bunch of ways to deal with this throughout the year. First fundamental theorem of calculus, using geometry, using numerical stuff, all those things. To be able to use any of those methods to compute this integral, two things must be true. First of all, the interval from a to b must be a finite interval. And what I mean by that is we can handle doing the integral from 1 to 4 of f of x dx. We couldn't handle the integral from 1 to, say, infinity of f of x dx. The second thing that has to be true for us to be able to evaluate a definite integral is our function cannot have an infinite discontinuity on that interval, otherwise known as a vertical asymptote. F cannot have a vertical asymptote on the interval that we're integrating over. So for example, I could do the integral from 0 to 2 of 1 over x squared plus 1 dx, but I couldn't handle the integral from 0 to 2 of 1 over x minus 1 dx, because there's a vertical asymptote at x equals 1. Improper integrals are our way of getting around these two issues. So first, to give you a definition, an improper integral is either an integral over an infinite interval, it's either an integral over an infinite, I didn't mean that, infinite interval, not integral, so something like one of those problems. Or it's an integral over an interval that includes a vertical asymptote. Like something over there. And actually, technically, an improper integral can also include both of these things at the same time, can be over an infinite interval, 0 to infinity, with a vertical asymptote in there. Not right now. Today, we're going to see how to deal with what happens if our interval is infinite. So how do we integrate from 1 to infinity? Next time, we'll deal with what happens if we try to integrate up to a vertical asymptote or over a vertical asymptote. To integrate an improper integral, over an infinite interval, Well, first of all, for what I'm about to show you to work, we need to assume that our function is continuous on that interval. So this is assuming f of x is continuous on the interval if I want to integrate from a constant to infinity, f of x dx, find the integral from 1 to infinity, or 5 to infinity, or negative 2 to infinity, or something like that. The trick is the same trick that I always do when I deal with infinity things. I need to turn this problem into a limit problem. I can make this the limit as b approaches infinity of the integral from a to b of f of x dx. If I want to do the integral from negative infinity to some constant, similarly, I can turn this into the limit as a approaches negative infinity of the integral from a to b of f of x dx. There is a third type. If I try to go all the way from negative infinity to positive infinity, well, I can't really do that. But instead, I can go from negative infinity to some sort of constant, and then go from that same constant to infinity, really just splitting up my integral at a convenient place. Then once I have that, well, to deal with this one over here, I'll use the ideas from number 1 over there. And to deal with this, I'll use the ideas from number 2. One more idea, and then the rest of the video will just be examples of how to work with this stuff. Our limits might exist, but our limits might also not exist. If the limit exists, we say that our integral converges. If the limit exists, the integral converges. If the limit doesn't exist, the integral, we say, diverges. If the limit doesn't exist, the integral diverges. Maybe my limit will be infinity or something. Then I'd have to say the integral diverges. Let me show you how to work with this. Okay, so first example we're going to take a look at is the integral from 2 to infinity of 1 over x squared dx. By the way, what is this asking us to do? Well, 1 over x squared looks something like that. I want to find the area from 2 all the way to the right. Does this actually approach some sort of finite area, or is the area here actually infinite? Well, here's how we can deal with this. According to the rule that I just gave you, we need to turn this into a limit problem. We can say this is the limit as b approaches infinity of the integral from 2 to b of x to the negative 2. Then this is a power rule problem. The limit as b approaches infinity of x to the negative 1 over negative 1 from 2 to b. That equals the limit as b approaches infinity of negative 1 over b plus 1 over 2. And then we finish this off. And of course, remember all of our good notation, things involving limits. Never plug in infinity like it's a number. Continue to use the limit symbol until we actually take the limit. This thing over here is negative 1 over a huge number. That's 0. We're going to get 0 plus a half. And our area is a half. And I think the real way to see this is if we did like a numerical thing on the calculator and did the area from 2 to 10, we'd get maybe like 0.48 or something. I'm just making up numbers here. If we went from 2 to 100, maybe 0.499. From 2 to 1,000, 0.49999. And the further and further we go out, the closer and closer this area gets to 1/2. So we can say that the limit of this area as that upper limit approaches infinity is 1/2. That's what we're finding with these. Let's take a look at the integral from 1 to infinity of 1 over x dx. How about you push pause and see what you can do with this one? Assuming you've pushed pause, you tried things, now I'm going to go. Limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Well, this isn't a power rule problem because it's 1 over x, it's a natural log problem. We'll do the limit as b approaches infinity of the natural log of, I'm not going to bother with absolute value bars because 1 and b are both positive things. Natural log of x from 1 to b. That's the limit as b approaches infinity of the natural log of b minus the natural log of 1. Okay, so the natural log of infinity, natural log looks like this. Oh, actually, you know what? Natural log of infinity, that's some sort of huge number. That's going to give us infinity. Natural log of 1 is 0, but what's a huge number minus 0? It's a huge number. My limit is infinity. Which means if you're trying to find the area under 1 over x from 1 to infinity, it just keeps getting bigger and bigger and bigger and bigger. What I'm going to say about my integral is my integral diverges, which is the better response than just saying infinity for something like this. My integral diverges. Let's try another. If we want to do the integral from 0 to infinity of e to the negative 3x dx. Well, first, we're going to write this with limits. This is the limit as b approaches infinity of the integral from 0 to b of e to the negative 3x dx. Well, what do we need to use? You just said use substitution. I know you just said use substitution. U is going to be negative 3x, and du is negative 3 dx. Limit as b approaches infinity of the integral from 0 to b. I'll stick a negative 3 inside, negative 1/3 outside. This is the limit as b approaches infinity of negative 1/3 times the integral. We need to change our limits of integration now. 0 becomes negative 3 times 0. b becomes negative 3 times b, or negative 3b. e to the u, and the negative 3 dx becomes du. Okay, well, when we integrate, this is the limit as b approaches infinity of negative 1/3 times e to the u from 0 to negative 3b. That's the limit as b approaches infinity of negative 1/3 e to the negative 3b plus 1/3 e to the 0. What is e to a negative huge number? Well, if you think about the graph of what e to the x looks like, it's one of those things. E to a negative huge number, though, is really close to 0. What is e to the 0? 1. 0 plus 1/3. Your answer is 1/3. So this is the basic idea behind how these improper integrals are going to work. I have two harder examples we're going to take a look at, and that should do it for today. Next example. The integral from negative infinity to 1 of x e to the 2x dx. Do your first step of rewriting this problem with a limit. No, it doesn't matter what letter you use. I usually use A for the bottom and B for the top, but no, doesn't matter. X e to the 2x dx. Use substitution won't get us there. What can we do with this? Did you say integration by parts, that product rule that we just looked at? Maybe you did. Hopefully you did. L-I-A-T-E. Here we go. I've got something algebraic. I've got something exponential. I'm going to say u is x. dv is e to the 2x. du is dx. v equals, well, we need a u substitution there. Maybe you can skip over that, though, and just go straight to 1/2 e to the 2x. And I'm going to go do my u times v minus the integral of v du. This gives me the limit as a approaches negative infinity of, let's see here, u times v, so 1/2 x e to the negative 2x minus 1/2 times the integral of e to the 2x dx. Well, integrate that again. Use substitution, or just realize it means we're going to stick another 1/2 out front. This is the limit as a approaches negative infinity of 1/2 x e to the 2x minus 1/4 e to the 2x. Oh, you know what I'm realizing? I forgot my limits of integration here. I'll do my a and my 1, my a and my 1. And then we're going to plug in. Although there's a little more to this than just that. Plug in 1/2 times 1 times e to the 2nd minus 1/4 e to the 2 minus 1/2 a e to the 2a minus 1/4 e to the 2a. Okay, let's see. This is going to give me e squared over 2 minus e squared over 4. And I think I'm just going to leave the rest for right now. I'm not ready to deal with that. I can subtract these. This is 2e squared over 4 minus 1e squared over 4. That gives me e squared over 4. And you know what? I don't really need the limit with that stuff, since they were just constant things not involving the a. I'm going to say e squared over 4 minus, you know what? Why don't I say the limit as a approaches negative infinity of 1/2 a e to the 2a plus the limit as a approaches negative infinity of 1/4 e to the 2a. Let me actually start with the second one, because I think that's going to be easier. What's e to a negative huge number? We saw that in the last problem. That's 0. So this limit over here is 0. Over here, e to a negative huge number, yeah, that's 0. But if I'm multiplying 0 by negative infinity, that's actually not okay. We've looked at a few indeterminate forms this year, 0 over 0, infinity over infinity. But 0 times infinity, or 0 times negative infinity, is another one of those indeterminate forms. We talked about indeterminate forms in relation to L'Hopital's rule, where we had 0 over 0 and infinity over infinity, I could use L'Hopital's rule. Well, it doesn't work on 0 times infinity or 0 times negative infinity. But if I could rewrite this problem in a way that gives me 0 over 0 or infinity over infinity, then I can use L'Hopital's rule. You know what? How about I take e to the 2a, make it e to the negative 2a, and stick it in the bottom? That'll give me e squared over 4 minus the limit as a approaches negative infinity of a over 2e to the negative 2a. Well, now this gives me negative huge number on the top, e to a negative 2 times negative infinity, e to a huge number on the bottom. Huge number on the bottom, this is a huge number over a huge number. It is now in an appropriate form for us to use L'Hopital's rule. Sometimes with these improper integrals, you'll get a limit looking like 0 times infinity or something like that. We need to rewrite it as 0 over 0 or infinity over infinity to be able to use L'Hopital's rule. Well, continuing with this stuff, I'm going to say, using my normal notation for L'Hopital's rule, since the limit as a approaches negative infinity of a equals negative infinity, and the limit as a approaches negative infinity of 2e to the negative 2a equals, okay, negative 2 times a negative huge number is a positive huge number, e to a huge number is a huge number, times 2 is infinity. Because they're both some form of infinity, I can say, by L'Hopital's rule, the limit as a approaches negative infinity of a over 2e to the negative 2a equals the limit as a approaches negative infinity of derivative of the top is 1, derivative of the bottom we need chain rule on, 2e to the negative 2a times negative 2, so negative 4e to the negative 2a. Well, now go to plug in a negative huge number. Negative 2 times a negative huge number is a huge number. E to a huge number is huge, times negative 4, negative huge number, but 1 over that is going to be 0. Oh, well, for just 0. Well, we've got e squared over 4 minus 0. The area under that thing is e squared over 4. One more. Let's take a look at the integral from negative infinity to infinity of e to the x over 1 plus e to the 2x dx. First of all, since this is of that third form, I need to split this into two different integrals. I need to find some sort of number between negative infinity and infinity. Well, obviously, I can choose absolutely anything out there, but let me choose something nice and easy, like 0. I can say that this is the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x dx, plus the integral from 0 to infinity of e to the x over 1 plus e to the 2x dx. I'm going to call this 1, mostly because it's just positive thing. It's going to be a little nicer to work with. I'm going to call this one 2. The idea is, let me figure out 1, get an answer. Let me figure out 2, get an answer. I'll add the answers together, and I'll have my final answer. So I want to do the integral from 0 to infinity of e to the x over 1 plus e to the 2x dx. Do your first step of just rewriting this with a limit. Hoping you said limit as b approaches infinity of the integral from 0 to b of e to the x over 1 plus e to the 2x dx. So this is a little bit of a tricky one. I need to do a u substitution here, but if you make u the whole denominator, then du is 2e to the 2x, not just e to the x. This is not super obvious, but what I'm going to do, e to the 2x, that's like saying e to the x squared. I'm going to make u e to the x. Du, then, its derivative, is e to the x dx. This is going to become the limit as b approaches infinity of the integral of, okay, I can say this top is du, and I can say the bottom is 1 plus u squared. And this is starting to look like a form that we dealt with at some point throughout the class. I do need to change my limits of integration. 0 is going to become e to the 0. That's 1. B is going to become e to the b. Well, that's e to the b. Do you happen to remember what the integral of this thing is? It's going to be the arctangent. This is the limit as b approaches infinity of the arctangent of u from 1 to e to the b. Well, I'm going to plug in limit as b approaches infinity of the arctangent of e to the b minus the arctangent of 1. E to a huge number is a huge number. What's the arctangent of a huge number? Well, let me take a look at the graph of tangent of x. I know that tangent of x has vertical asymptotes at pi over 2 and negative pi over 2. So if I'm asking what has a tangent of a huge number, it's that angle over there. It's pi over 2. What angle has a tangent of 1? Hopefully you were thinking pi over 4, because sine and cosine are the same there. Subtract 2 pi over 4 minus 1 pi over 4 gives us pi over 4. Not the final answer, but I'm halfway there. The other half. To do the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x dx, we'll make this the limit as a approaches negative infinity of the integral from a to 0 of e to the x over 1 plus e to the 2x dx. Of course, it's the same u substitution. U is e to the x, du is e to the x dx. So it'll give us limit as a approaches negative infinity of, let's see, plug in a, you get e to the a. Plug in 0, you get 1. This is du over 1 plus u squared, just like it was on the top. Integrate, we still get our arctangent. So this is arctangent of u from e to the a up to 1. Limit as a approaches negative infinity of the arctangent of 1. I think I need a new pen. Arctangent of 1 minus the arctangent of e to the a. Arctangent of 1, still pi over 4, minus, well, if you plug in a negative huge number, e to a negative huge number is 0. This is the arctangent of 0. And what angle has a tangent of 0? 0. So we're going to get pi over 4 from that. Going back to the original problem, if I want to do the integral from negative infinity to infinity of e to the x over 1 plus e to the 2x dx, I'm going to do pi over 4 plus pi over 4, and the area under that thing will end up being pi over 2. I think that this one was a little bit of a stretch. I think the homework is a little bit more like the rest of the examples. But I think that's all I have to say. And next time we deal with class, we'll deal with what happens with trying to integrate up to a vertical asymptote or even over a vertical asymptote and how to get around that issue of improper integrals. See you later.